Welcome to Maths with EJD. We still continue with numerical solutions to algebraic equations, particularly talking about solutions to systems of linear equations, for which we have identified two broad categories of methods. We have some, they are direct methods. We have other ones that are iterative in nature. So far, we've dealt with all the direct methods made up of Gaussian elimination. Then we've talked about LU decomposition that decomposes the the coefficient matrix into the product of a lower triangular and upper triangular matrix. That's why we have LU, lower upper decomposition. And then we have the Cholesky decomposition. So the Cholesky decomposition actually factorizes the coefficient matrix into the product of a lower triangular matrix and its transpose. Okay, and that is why Cholesky decomposition is only useful when the coefficient matrix of whatever problem you're solving is symmetric and positive definite. So you have to check for the symmetricity and the positive definiteness before you start doing anything in that situation. So for the iterative methods, we have Jacobi method, we have Gauss-Seidel, and we have successive over relaxation. Okay. And so far, we have taken care of Gaussian elimination, LU decomposition, Cholesky decomposition. Then in the last video, we talked about Jacobi. Now we are going to check Gauss-Seidel, which is actually an improvement on the Jacobi method. And you're going to see how it is an improvement in a moment. Let's go. Now, we have the Gauss-Seidel method. Gauss-Seidel method. Like I said, it's an improvement on the Jacobi method of solution, which is also iterative. So the Gauss-Seidel method is an iterative technique for solving a system of linear equations that improves, like I said, upon the Jacobi method by using the most recently updated values as soon as they are available. So remember the other time, we needed for x1, we needed x naught, y naught, and z naught. And for y1, we needed for y1, we needed for x1, we needed y naught and z naught. For y1, we needed x naught and z naught. For z1, we needed x naught and y naught. And then for you remember for x1, right? You would need for y1, you would need just the initial thing you have. But in the case of Gauss-Seidel, as soon as a value is available, you use it. So for instance, uh once you get x1, by the time you're going to look for y1, you use the x1 you found just now, you use it in y1, and that helps to make the problem convert pretty fast. Okay. So updated values as soon as they are available. So once a value is available, you use it immediately. So let's talk about the general formula in this situation. The general formula for each variable, x sub I at iteration n plus 1 is what you have down here now. So you have xi n plus 1 equals 1 over aii into bi minus summation j less than I, aij, xj. Now, as soon as x is available, so you use that n plus 1 immediately. They are the same level now. But then any value that is not available, like if at y now, at y, z is probably not available. And that's for j greater than I now. So for values ahead of the current place, it wouldn't have been available. So you use the previous one. So you have aij, xj, n. So, it's a, so as soon as x, so something is available, you use it straight. That's what this is about. Where, again, aii is the diagonal element, of the coefficient matrix. So that's what you have outside of the bracket, like we did under Jacobi. Then you have aij. As usual, they are the off-diagonal elements. Then you have the BIs, of course, that's the right-hand side, the constants. So these are the constant terms. Then you have xj n plus 1. You might say that xj or even xi n plus 1, right? Yeah, xj n plus 1 will be the newly computed values, and that's how Gauss-Seidel is different from Jacobi. Newly computed values. Then you have xjn, which will be the previous iteration values. Okay. And don't forget, usually, right, we have initial condition. You have initial condition. You may be given, and if you're not given, you can just choose them to be 0, 0, 0. That's the most convenient. You can just choose, but you may be given something different. So you have to be careful to choose your initial condition. Just to choose it as 0, 0, 0 if you're not given. Then, of course, there's also the convergence criterion, or the stopping rule, if you like. Convergence criterion, or the stopping rule. How do you know when to stop? Just like we did for the things like LU decomposition and everything. No, or even for root finding. Yeah, for root finding that involved iterations, right? For each root you find, you compare it with the previous one and see how close they are. So if the absolute difference between them is less than the tolerance limit, then you're good to go. So the convergence criterion again here is absolute value of xn plus 1, yn plus 1, zn plus 1 minus xn, yn, zn. You compare them pair by pair. So xn plus 1 and xn, yn plus 1 minus yn, zn plus 1 minus zn, and see if it's less than epsilon, where epsilon is the tolerance limit, okay? But in this case, like I said, I won't bother so much about that. I'll just do maybe 3 or 2 iterations and then direct it to the Python code so you can see if the method works very well. So now that we have explained this, can we go straight to the example we've been solving with all the different methods? Same example, because I want to compare the methods at the end of the day. So the example again is to solve x plus 2y plus 3z equals 9, then 2x plus 5y plus 6z equals 18, and then we have 3x plus 6y plus 14z equals 30, okay? Using Gauss-Seidel method, that is. So let's talk about the solution. So the solution here is now this. Again, I mean, I'll just go straight since we have the problem up there already and it's not even new. We've always used it in previous for previous methods. So I'll just go straight and explain it just like Jacobi, except that as soon as you get a value, you use it in the next place. So for this now, you have x plus 2y plus 3z equals 9. Now, for the first one, you need x, right? So that implies that x is equal to 9 minus 2y minus 3z. So if you're going to form a formula from this, so that formula is going to be, say, xn plus 1 is equal to 9 minus 2yn minus 3zn. So that is the formula we are going to use for this. Now, from here, before you got here, right, all we had was xn, or whatever, or maybe x naught, right? So by the time you go for the next one, the second equation, which is 2x plus 5y plus 6z, of course, we know that's going to be of y is in contention now. So we have y to be equal to, oh, okay, I've not completed that. All of that is equal to 18. This is equal to 18. So this implies that y is equal to 18 minus 2x minus 6z. Okay, divided by 5, right? So the 5 comes out. So the coefficient of y is 5. So we have 1 over 5 into 18 minus 2x minus 6z. So if you want to establish the formula for that, that will be yn plus 1. Now, because you have computed xn plus 1 here, you just use it immediately. So you have yn plus 1 equals, and that's the difference between it and Jacobi. So 1 over 5 into 18 minus 2xn plus 1 minus 6zn, because you don't have zn plus 1 yet, so you use the old one. So this is basically the difference between Jacobi and Gauss-Seidel. Okay. All right. So we move on to the next one. So move on to the next one. So you take the third equation again. That is 3x plus 6y plus 14z. So the focus is on 14 now. All of this is equal to 30. So, this simply implies the coefficient of z is 14. So it means z is equal to 1 over 14 into 30 minus 3x minus 6y. Okay. So that means that the formula for that is going to be zn plus 1 equals 1 over 14 into 30 minus 3. Now you have xn plus 1, and you also have yn plus 1, because you have yn plus 1 here now. Okay. And you have xn plus 1 here. So as soon as the value is available, you just use it straight. And with that, so you have an improvement on Jacobi, and it makes the problem converge faster. Okay. So let's start the iterations. Let's do the first iteration. So let's go for first iteration. So that's where we find x1, y1, z1. So we have x1 now equals, from the expression we have here. So if n is 0, so we have x1 equals 9 minus 2y naught minus 3z naught. Okay. So x1 is 9 minus 2y naught minus 3z naught, and that is equal to 9 minus 2 into 0 minus 3 into 0. So this cancels out. So we see that for that, x1 is equal to 9. So we have that straight up. So we go for the next one, which is y1. So y1 now, just like we said, it's going to be, so we already have the expression. Y1 is 1 over 5 into 18 minus 2x n plus 1. So that is 1 over 5 into 18 minus 2x1. So you see, x1 is now at the same level because you have found x1 here, so you use it straight. So minus 2x1 minus 6z naught, because you don't know z naught yet. So that will be, because you don't know z1 yet, actually. So you have 1 over 5 into 18 minus 2. X1 now is 9 minus 6. Z naught, the z naught you started with is 0. So you use that just the way it is. So this cancels out. So if you punch your calculator properly, so y1 is going to give you 0 for sure, because 18 minus 18 is 0. So everything just goes 1 over 5 times 0 is 0. So y1 is 0. So you can see the ultimate answer is 0 for y. if you remember the solutions we've been getting. So you can see that Gauss-Seidel is already giving us something close to the answer. X1 is actually 7.2, and we have 9 here. Not like Gauss-Seidel that gave us something that I think a bit far away or something like that. So then we can go for Z1 also. Z1 now is from what we have. So everything is at the same level. So Z1 is 1 over 14 into 30 minus X1 minus Y1 minus 6Y1 because we have X1 and Y1 already. So Z1 is 1 over 14 into 30 minus 3, 30 minus 3X1 minus 6Y1 like this. So that's 1 over 14 into 30 minus 3 into X1. X1 is 9. Okay. Minus 6y1. Y1 is 0. That's just what we got. This is just the y1 we got now. So for this now, you have 30 minus 27, that's 3. 3 minus 0, of course, this is 0. So that's 3. So this just gives us, okay, let me do what I've been doing. Now we have Z1 to be equal to 3 over 14. And 3 over 14 is the same thing as 0.2143. So that's Z1 right there. And that completes the first iteration. That completes the first iteration. So we move on to the second iteration. Second iteration. So for the second iteration, we start again. We have x2 x2 is equal to 9 minus 2y1 because we don't have y2 yet, minus 3z1 because we don't have z1 yet. And that is equal to 9 minus 2. Y1 so far is 0. Then minus 3 into z1. Z1 is 3 over 14. You know, I like using fraction to preserve the value, but you can use the decimal too. You can use 0.2143. That you get almost the same result. So here now, we can then say we have x2 to be equal to, 9 minus 0 minus 9 over 14. All of that goes to, x2, that's 117 all over 14. Okay, 117 over 14. And that is the same thing as 8.3571. So, the x1 was 9. So you can see this is converging towards the answer, which is 7.2 ultimately, right? So you can see this method looks, it's getting closer, right? Then we go for we go for y2. So now that we have x2, we are going to use x2 straight for y2. So for y2 now we have 1 over 5 into 18 minus 2x2 straight, not x1 anymore. But we don't have z2 yet, so we just have 6z1. And that means we have 1 over 5 into 18 minus 2. What is x2? x2 is 117 over 14, because I like to use fraction, minus 6 into z1. So the last z1 we got is still 3 over 14. Okay, that's 3 over 14, like that. And that gives us y2 to be equal to, if you punch your calculator correctly, interestingly, that's going to be 0 again, and that's lovely because 0 is actually the final result. So we have, for y2, the result is like already converged, but the other ones have not. So we are still moving. So then we go for z2. So for z2 now, z2 is simply the 1 over 14 into 30 minus 3x2 because we have x2 now, minus 6y2 because we have y2 now. So that's 1 over 14 into 30 minus 3 x2 like we got is 117 over 14, 117 over 14 minus 6. Y2 is 0. Lovely to know that. And then we have z2 is equal to, if you punch your calculator correctly, z2 is 69 over 196, and that is the same, approximately 0.3520. Normally, I should be writing approximately like this, 0.3520. And that completes the second iteration, right? So we go for the third iteration. So we have the third iteration. So the only difference is that, and as soon as you get a value, you can use it in the next, for the next variable. Basically, that's the idea. So now you can see this is 0.320. When we start, the first Z1 was 0.2143. So now this is, and we know the original answer is 0.3, 0.6. So you can see this is moving up to meet 0.6, while the x, which was 9 before, is moving down to go and meet 7.2. While while y is already 0, which it's supposed to be. So we go for the third iteration, which means that x3 is equal to 9 minus 2y2 minus 3z2, and that is equal to 9 minus 2. Y2 is 0. We just got like up then. Y2 is 0 minus 3. Z2. Z2 is 69 over 196. Please feel free to use the decimal if you don't have a calculator that can handle fraction. So, and here we have x3 to be equal to, I think x3 is now 1557 all over 196. You don't have to get this fraction. Just use your decimal if your calculator cannot handle this. So you can see the value has reduced further to 7 point. The value has now reduced to 7.9439. So you can see it's converging. Whereas Jacobi wasn't converging this well, then we can go for y3. Now that you have x3, you can use y3 here directly, and that is 1 over 5 into 18 minus 2x3, which you just got now, minus 6z2, which you don't have, since you don't have z3 yet. So you have 1 over 5 into 18 minus 2 into 1557 all over 196. I like to use fraction. Feel free to use decimal. That's why I also supplied that. So 6 into Z2. So the Z2 now is 69 over 196, or you can use the decimal 0.3520. So 69 over 196. Okay. So punch your calculator good, and you have Y3 equals, Y3 is 0. Okay. So you can see that one has already converged, whereas X3 is dropping to go and meet 7.2, while Y3 is increasing to go and meet 0.6. So although we have not got Z3, let's do Z3 now. Z3. So since we have X3, Y3, so we can use them here. So for Z3, we now have 1 over 14 into 30 minus 3x3 minus 6y3. Okay. And that is 1 over 14 into 30 minus 3. X3 is 1557 all over 196. Feel free to use decimal if this fraction does not work for you. Minus 6 into 0. Okay. So X3, that's 1557 over 196. Y3 is 0. So punch your calculator very well, and Z3 jumps out at you to be 0.4406. Oh, okay. Before I even do that, I like the fractional part, right? So that is 1209 divided by 2744. And that's approximately 0.4406. So you can see Z3 again has increased because it's converging towards 0.6, which should be the actual answer. Don't forget again that what do we call that now? Actual result is such that you have x to be 7.2, that's 18 over 5. You have y to be 0, and you have z to be 0.6. Okay, so we can complete the rest with Python code, right, to know the number of iterations this will require. And of course, that'll be dependent on the value of f of epsilon. So let's go for that and see how Gauss-Seidel ends the story. Now, okay, we've seen Jacobi before, so this is Gauss-Seidel right here. So you can feel free. I'm not able to put this code uh in the description box for YouTube, but if you go to Facebook, you can check the caption under Gauss-Seidel. You're going to find this code there, so you can study it and adapt it to any problem you may need to solve. So I think the key thing is where you define the matrix. So you see the matrix has been defined. If I do view and I put the line numbers, right? So the matrix is defined from line 9 to 11. So so you can redefine your matrix and fix the tolerance limit. Now the tolerance limit here is pretty high, so we want something really accurate, and we have maximum of 1000 iterations. So anyone that is reached first. So just in the case of Jacobi, we reach the number of iterations first before the tolerance. So Tolerance didn't really matter. But normally, if the problem is converging, then the tolerance can kick in. So just study the code and I'll just run that and see what it gives us. So it finally goes to x, which is 7.2 something something, and y, which is zero point 0.0, which we got of maybe as at the second iteration or so. And for z, we have 0.5999, which is very close to zero point 0.6, which the correct answer is. But guess what? And all of this is attained after 54 iterations. Okay? So 54 iterations, and that's because of the tolerance limit. If I make the tolerance limit the normal 0.01 we've been doing, so let's see what happens. So in 12 iterations, we get 7.2 something, we get 0.0, and this is 0.59. So I mean, so if we're going to do it manually and I have a tolerance of 0.01, so I'll do what I'm doing now. This Y3 I have, I'm going to have Y12 before we get something this close, So, but that's why coding just helps and does a neat job like that. So that's why I want to note the two together. All right. So thank you for listening to this video on Gauss-Seidel method. Get a question and practice to see how well you understand this. In fact, I think I've been giving out a practice question. Let me, or I can, or maybe I can afford to. So let me go back and write it so you can try your hands on this. Yeah. So let's do that. Practice questions. Okay, practice questions. So you want to solve these two questions. The first one is U plus 2V plus 3W equals 1. Then you have 2U plus 5V plus 6W equals 3. Then you have 3U plus 6V plus 14W equals minus 2. That's question 1. And for question 2, you can try this. 2P plus 3Q minus 4R equals minus 4. Then P plus Q plus R is equal to 9. And then P minus 2Q plus 4R equals 15. So try this using all the methods you have ever learned and see how well you have mastered the methods. Okay. So if you have not subscribed to this channel, feel free to do that right away. If you have, thank you very much. And hit the notification bell so that you can always get alerted each time a new video is released. Then comment, show me your results in the comment section, and also let me know how helpful these videos are. Let me know if there's a problem you'd like me to solve or a topic you'd like me to teach. I may be able to find time along the line to do all of that. Then like and share so that more people can have access to this great content. Like, come your way again. Keep doing maths right. Bye.